This lesson deals with a CMOS transmission gate. You can find these notes in the ECE302 ebook in Chapter 4, starting on page 46. Some of our previous videos, I talked about the bulk pin being connected to the positive power supply and the most negative potential in the circuit. Let's take a look at why. In our past applications, we've been looking at a 0 5-volt power supply. In other words, a positive supply, and then the most negative supply is 0. But it's possible to have negative supplies, so in other words, a plus 5 and a minus 5. Take a look at a N-channel device, side cut. This is like the picture on page 10 in this chapter. And I have a bulk, which is made out of P material, and then I've got a drain and a source that's made out of N material. I've got a PN junction between those two nodes in the circuit. The voltage across this diode is V sub BD. This is the bulk to ground minus the drain to ground. Likewise for this diode, it's between the bulk and the source, it would be the bulk minus the source voltage. Now suppose that we had a negative power supply that was 0. Then the bulk to drain would be the following, the bulk being 0, but now the drain can go between 0 and 5 volts. The difference of those two, if this was 0 volts, would be 0. If this was 5 volts, it'd be a negative voltage. For all possible values of the drain with a plus power supply and a ground is always less than or equal to 0. The same is true for the bulk to source because, again, the bulk is hooked up to ground, the most negative potential in the circuit, and then the source can swing between 0 and whatever the positive power supply is, say 5 volts. This is always a negative number. Now suppose that the most negative potential in the circuit is, say, minus 5 volts. In other words, less than 0. Now, the difference of these two would be we're going to tie the bulk to minus VDD, and then the drain can swing now between plus and minus the power supplies. Let's just use 5 volts again. Suppose this is 5 volts, I got minus 5, and now minus the swing of this, if it was plus 5, we'd have minus 5, or minus 10. This could also swing to a negative 5. Now that would make that a positive number. The difference would be equal to 0. And we never have a voltage greater than 0, whether we have a single power supply or a dual power supply, and therefore we can't forward bias this diode, and the same is true for the bulk to source diode. And that's why we're going to tie the bulk pin of an N-channel device to the most negative supply. The way I remember that is that it's an N-channel and the most negative power supply, two N's. Let's see about the P-channel device. Here the bulk is equal to N material, and the drain and source are P material, so I've got a diode between these two pairs of nodes. The voltage across this diode is from the bulk to the drain, the difference of those two node voltages, and then likewise here, the source to bulk, difference of those two. If I tie this to the most positive potential in the circuit, that's going to put this over here. Whether I got a plus or minus 5 volts or 5 volts and 0, it's just going to be the positive power supply. So I got a minus, say, 5 volts here. If I had a 0 to 5 volt power supply, this could swing between 0 and 5 volts, but I'm always subtracting 5. That's going to always be less than or equal to 0. If I had a dual supply, this could go down to minus 5 volts, but then I'd have minus 5, and less than or equal to 0. So I can't forward bias this diode. The same is true for the source to bulk diode. We're tying the bulk to VDD, so we're going to get a negative of that. And again, this could swing between, say, minus 5 and plus 5, but in any case, this will always be less than or equal to 0. You can't forward bias these diodes in either case if we take the N-channel device's bulk and go to the most negative potential in the circuit, or the P-channel, go to the most positive. Here we have the schematic of a transmission gate. It consists of an inverter that's here, and then two transistors on the outside of this. I'm going to label the nodes A, B, C, and then I'm going to draw this as a rectangle, where A is the input, B is the output, and C is going to be a controlling voltage. Notice here that the bulks of the P-channel devices are hooked up to the most positive power supply in the circuit, and the N-channel devices are hooked up to the most negative potential in the circuit. Let's use a plus and minus 5 volt power supply in this example. For this circuit, I'm going to have an input that can be an analog signal, and I can swing between the power supply pins to plus 5 and say down to minus 5. Suppose that I put a voltage here of 5 volts. This would be a logical 1 in a 5 minus 5 volt system. What is the gate to source voltage? Well, it's going to be 5 volts minus a minus 5, so 10 volts. And what is the source to gate voltage here? It's going to be 5 volts minus 5 volts, or 0. Now let's assume that the threshold voltage for all these transistors is about 1 volt, just to make the algebra easier. Here I'm greater than threshold, and here I'm less than threshold. So you can think of this as a resistor that's going to be high or low, but since I'm greater than threshold, I'll think of this like a short circuit, and this like an open circuit. So the voltage here, if this was shorted, would be equal to minus 5 volts. and this were open. And again, this is an inverter, and that makes sense. Logical 1 in, a logical 0 out. Suppose that my input signal is just slightly positive, so I'm right over here, say. What's going to happen? Let's figure out the gate to source and source to gate voltages. So what's the gate source voltage here? Well, it's 5 volts, and then minus the input, which is roughly about 0, about 5 volts here. Over here, the source is equal to roughly 0, and the gate is hooked up to minus 5. So 0 minus a minus 5 is about 5. The gate to source and the source to gate are both the same value. And you can think of these as resistors between here and here. They're about the same value in resistance if they were identical transistors. Suppose the value of that's maybe, say, 10 ohms. My analog signal is coming in, starting out at a little bit positive. What's the output voltage? Well, suppose that the load is 10K. Where it's much bigger than the 10 ohms. I got a voltage divider of 10K over 10K plus 5, these two equal in parallel, times Vin. Pretty much a gain of 1. I'm passing the signal by putting a logical 1 on the control line. Suppose my input now is 3 volts. Let me erase this and this over here. What's my source to gate voltage now? Well, it's 3 volts here minus a minus 5, so that's 8 volts. What's the gate source here? Well, it's 5 volts minus 3 volts. That's 2 volts. My source to gate voltage went up, and my gate to source voltage went down. Let's go back to page 12 and see what happens. I have a particular value of gate source voltage, and if I were to make it larger, I would be on this line over here. And the resistance is going to go down because this is a slope of conductance. As we move in this direction, this is a lower resistance than it is over here. If the voltage across the gate source gets smaller, then the resistance goes up. Let's go back to page 47 again. For my P-channel device, I now have a source to gate that's greater than it was before, so now the resistance here is going to go down. So it's something less than 10 ohms. I don't know, maybe say it's 5 ohms. And the value of the gate to source here went down, so the resistance is going to go up. So it's now going to be greater than 10 ohms. I don't know, maybe say it's 20 ohms. Now my output is going to be my input, which is 3 volts, times a voltage divider of 10K over 10K plus the parallel combination. Now when you had 10 in parallel with 10, you had 5 ohms. But now I've got 5 in parallel with 20, and it's going to be a little bit smaller than 5. Even though things have changed, my voltage divider stays the same. I basically pass the signal because these resistors, although they're changing, are smaller than the resistance here. But note that what's happened is that one's going down and one's going up, and of course the parallel combination is the smaller of the two. Suppose I were to go to 4 volts. That would make this 9 volts, and that would make this 1 volt. Would have this resistance going down some more because now we have a bigger voltage here, and this one would be going up more. We're actually at the threshold voltage. And I've got a voltage divider of 10K with something smaller than 5. We're passing the signal. What happens when the signal goes negative? Suppose that we're sitting here at minus 1 volt. Now what is the source to gate voltage? We have minus 1 volt minus a minus 5, so we have 4 volts here. Here we've got 5 volts minus a minus 1, so we've got 6 volts here. Now, when they had equal voltages, we had 10 ohms and 10 ohms. This has gone down, so now I'm greater than 10 ohms, and this one's gone bigger, so it's going to be less than 10 ohms. When I've got something smaller than 10 in parallel with something bigger than 10, it's going to give me something that's less than 10. Which divided with 10K, 10K over 10K plus whatever this turns out to be times the input, and we can pass the signal. This is pretty much like a relay, but it's not mechanical, and that this will last a lot longer than a mechanical device that's switching mechanically on and off. Let's take a look at what happens when I change this to a logical 0. To do that, I need to erase everything again, so let me do that. Suppose now we put a logical 0 here, which would be minus 5 with a plus and minus 5 volt power supply. What's the gate source voltage here? Well, it's minus 5 minus a minus 5, so that's 0. That makes this an open circuit. And what is the source to gate here? Well, it's plus 5 minus a minus 5, so that's going to be equal to 10 volts. It's a very low resistance, so we're basically shorting these 2 points together, opening these two. This is about 5 volts. This is an inverter, so logical 0 in, logical 1 out. Let's now analyze our analog signal. Suppose that we have a slightly positive voltage here. So what is the source to gate voltage equal to? Well, it's roughly 0 minus 5, so roughly minus 5. Here we've got minus 5 minus 0. We've got also a minus 5 volts here. Less than threshold, less than threshold. These are very big resistors. Suppose they are, say, a gigaohm. Now I have a voltage divider of my input, slightly positive number, times 10K over 10K plus a half a gig. It's a very, very small number. My voltage divider is close to 0. As long as this is much, much bigger than this, then we get this voltage division with a very small output. What happens now if the input were, say, 3 volts? So if I have 3 volts here, so I have 3 volts minus 5, that would give me minus 2. Over here I have minus 5 volts minus plus 3. So I have minus 8 volts. Both are less than threshold. Basically block the signal again with 2 very high resistors here. Take a look at going to a negative voltage. Suppose this is equal to minus 1 volt. Here we have minus 1 volt minus 5, so I get minus 6. Over here I have minus 5, and then minus a minus 1, so that would give me minus 4. But in both cases we're less than threshold, so again we're very high resistance. This is modeling basically an open circuit. And my voltage divider stays the same. I pass very little of the signal with a voltage divider that's dominated in its denominator by a very, very large number. When you apply a logical 1 to the control pin, the output equals the input approximately, if the load is much bigger than the on resistance of the transistors. And if I put a logical 0 here, then I get a voltage divider again that basically blocks the signal as long as my load is much, much smaller than my value of my off-state resistance. And this is how a transmission gate works.